Hello and welcome once again for another ES340 video. This is day 15 example problem 2. So we have a dual turbine system here with a reheater and a bunch of properties obviously at each of the places, right? 1, 2, 3, 4. Okay, so steam enters a two-stage turbine with reheat operating at steady state as shown above. The steam enters turbine 1 with a mass flow rate of 120,000 pounds per hour at a pressure of 1,000 pound-force per inch squared and a temperature of 800 degrees Fahrenheit, and expands to a pressure of 60 pound-force per inch squared. From there, the steam enters a reheater where it is heated at constant pressure to 350 degrees Celsius. 350, yeah, it is Celsius. Okay, so we'll have to do conversion there. Before entering turbine 2 and expanding to a final pressure of 1 pound-force per inch squared. The turbines operate adiabatically, so there's no heat transfer, right? Remember what the words mean. With isentropic efficiencies, so the efficiency, assuming this is the isentropic efficiency now, not the regular efficiency. And the isentropic efficiency, remember, is relative to if there was no entropy change, right? If there was no change in entropy, this is what the state would have been versus what the state actually was, right? So the isentropic efficiencies of 88% and 85% respectively determine the net power developed by the two turbines and the rate of heat transfer. So up here we have, it's asking what's the net work that was developed here, and what is this this heat transfer into the reheater value. Okay, and again, immediately we should be thinking in terms of the energy balance equation, right? The energy rate balance equations. We should be thinking about that. And also, we should be thinking in terms of the isentropic efficiencies here, which are going to help us determine these things, right? So, recall for the isentropic efficiency that we know these couple of details. First, that W dot, let's call this turbine 1, so tur 1 over M dot. This is operating at steady state, so M1 dot is going to be equal to M2 dot equal to M3 dot equal to M4 dot, right? Because this is just a single flow here. Since there's a single flow, there's only single inlet, single exits at each of the places. Obviously, then, in that particular scenario at steady state, we're just going to have an M dot. We'll call this equal to M dot, right? For isentropic efficiencies here, that's going to be equal to H1 minus H2. This is just the energy rate balance equation. We'll get to the into the isentropic efficiency as well. But remember that the isentropic efficiency said that eta, let's call it isentropic, just so we can recall what that would mean, what that would be. This is going to be obviously H1 minus H2 divided by H1 minus H2S. Remember, that was the trick for isentropic efficiencies here, and which was the same thing as the work of the turbine 1 divided by m dot divided by the work of the turbine isentropic. Oops. Which we denote with an S here. That's the isentropic one. Okay? That's the difference between these two. So now we're going to get an actual example where you can find H2S. It's not terribly difficult, but we do need to be able to do that, and so we'll get there. The same thing's going to happen for turbine 2. That's going to be equal to, well, let's go back up to the turbine. We had 3 as the inlet and 4 as the exit for that one. So that's going to be H3 minus H4 over H3 minus H4S. Okay, at the isentropic state. So that's the isentropic efficiency of the second turbine. Again, if I write the energy rate balance equation, I'm just gonna, just like I did here, I'm just gonna skip to the end result. You can work through this and as I've done in previous problems and figure out how you get to this. But this is really just going to be H3 minus H4. Right, and then the final thing is, again, the energy rate balance equation for the reheater. If I do the energy rate balance equation for that one, I'm just going to skip to the end result because, again, you should be able to figure this out. But that's going to be over m dot, and remember that at steady state, of course, these all 3 of these are at steady state, so it's equal to 0, right? And it's, you know, q dot minus w dot plus the sum of the inlets, the mass flow rates times the inlet enthalpies and the kinetic energy and potential energy terms, right? But we said we could ignore those. So this is going to actually be equal to, well, in this case, because of how, because it's at steady state and how the equation works out, it's actually going to be the exit minus the inlet, right? The opposite of the work we should find. So it's going to be H3 minus H2. Okay, so those are going to be our 3 equations that we're going to need. And we already know what the mass flow rate is because it's at steady state, so we're good there. So the question becomes, how do we find each of these terms? Well, the nice thing is you were given these eta, you were given the isentropic efficiencies of each of these. Okay, so if I wanted to find all of the H values, obviously one thing that I can do is I can go to the states and figure those out, which I'll do in a second. But the other thing is that I can actually solve for some of them directly. So let's look at what ones we have enough information for. We have enough information. Remember, you need for the purposes of this course, we always need 2 properties on the tables, with the exception of the ideal gas tables, right? So we need 2 properties, P1 and T1. That's going to be at state 1. This is at 3, excuse me. So we know 1 and 3. So that means what we're going to really be looking for is we have enough to find H1 and we have enough to find H3. but we're really going to be looking for some way to find H2 and H4, okay? So let's write these in terms of things that we'll be able to find directly from the tables first, and then after we do that, we can work backwards, find all of those properties right off of the tables. So we know what eta turbine 1 is. I'm going to drop the isentropic, but remember that it's the isentropic efficiency. That's why that equation was the way that it was. But for turbine 1, times H1 minus H2S, I think, right? As I recall. Yeah, that's how we wrote it. Is equal to H1 minus H2. Now we know we'll be able to find H1. So what we're going to look for is H2. So if I rearrange this, I can get H2 is equal to, I just moved H2 over to this side, and I'm going to move the turbine thing over to the other side, right? That H2 is equal to H1 minus eta turbine 1, which was 88%, I believe, times H1 minus H2S. We'll get a similar equation for H3, right? We're gonna, or sorry, for H4 is what we're gonna be looking for in that case. We'll get a similar thing for H4. Equal to H3 minus eta turbine 2 times H3 minus H4S. Great. Now, what we're going to do, remember isentropic, just hold this in your head. Isentropic means that the entropy stays the same across these processes. So across the turbines, it's isentropic, right? That's why we were given these isentropic efficiencies. Okay, so then what we need to do is we need to find, now we need to actually go to the tables and find the states as given. This was intended to be Fahrenheit, by the way. That's why I got tripped up on that. That should have been Fahrenheit. At least the way that I went about solving the problem, that's the assumption that I made. So that should have been Fahrenheit. I apologize. Finding H1 off of the table, and this one came from, if you go and check the properties, let's look at what we have. P1 is 1,000 pound force per inch squared. And T1 was equal to 800 degrees Fahrenheit. This is superheated. So I'm going to use the superheated tables, which are table A4E. By the way, steam always means water. Okay, so it's always a a vapor state of water. Could be the superheated vapor, could be saturated, but in any case, it ends up being superheated in this scenario, just by going and checking. And so H1 then, reading right off the table, is 1388.5 BTU per pound. And since we're talking about isentropic, that should probably clue you in that we're probably going to need the entropy as well. And that's easy enough to also read right off the table. Times degree R, ranking. Okay, So then that, since it was isentropic going across each of the turbines, what that means is that S2 then has to be equal to 1.5665 BTU per pound times degree R. And we know that going back, P2 was 60 pound-force per inch squared. Okay, so P2 is equal to 60 pound-force per inch squared. And essentially what you find is that this value of S, and if you go to the pressure tables, so you go to, say, table A3E, then you find that this has to be a mixture, right? The S, this value of S is in between, in between the saturated vapor and the saturated liquid value. So that tells us that we're in a mixture. So immediately that should make you say, okay, I need to find the quality, because what I'm really looking for is H2, right? Remember all of the terms here that I'm looking for. I need H2, I need H3, 4, and 1, and also the values of H2S. So in this case, we're assuming that it's isentropic, right? Because we're assuming that it's isentropic, that's going to be my H2S value. But first, let's get the quality here. So that's my S2 minus SF divided by SG minus SF, right? This is just the way we find quality as usual. And what I find is that I am, if I substitute in those values, 1.5665 minus 1.2170, that's my SF. My SG is 1.6443 minus 1.2170, so that's my SF in that case. Again, which approximately comes out to be 0.8062. That's my quality. So my H2S state, remember, this is assuming isentropic here. That's why that's my H2S state. It's not my H2 state. My H2 state will be able to find using this equation, right, from our turbine efficiency. But my H2S state, because we assumed it was isentropic, is going to be equal to HF plus X2 that we had over here times HG minus HF, right? And that's the value, the corresponding values to these ones for the enthalpies, right? So this ends up being 262.2 plus 0.8062 times, and I'm just gonna move it down here because I obviously didn't leave myself enough room. I apologize. 1178. That's my HG minus my HF, which is 262.2. And if I work that all out, that means my H2S, right? Assuming that it was isentropic. That's what all of those values here mean. When we use the terminology with S, 2S or 1S or 3S, whatever, 4S, whatever the case may be, when we use that S there, that means we assume that it was happening isentropically. But my H2S then becomes 1000.5 BTU per per pound. Okay? And that means that my H2 then, we have the equation up here, I'll rewrite it down here, was H1 minus, well, let me actually rewrite the whole thing. H1 minus the eta turbine times H1 minus H2S. Times H1 minus H2S, which is this value that we had right here for the 2S, right? So that means H2 is going to be equal to, well, my H1, which was 1388.5. The eta of the turbine, that was 88%, which is 0.88, times the 1388.5 again, minus the 1000.5 that we found up here for H2S. And that gives me 1,000, or approximately 1,047.06 BTU per pound. Okay, so that's my H2. Now for state 3, recall that P3 was equal to 60 pound force per inch squared. T3 was equal to, I assumed that it was Fahrenheit for this problem, so I apologize that I missed that it was Celsius and didn't convert, but that's okay. Obviously, we'll just work through it this way. And in any case, it works out nicely this way, so that might have been the way it was intended anyways. So I can read this directly off the table, and off of the table I get H3 equal to 1208. This is superheated, by the way. A4E is the table that I'll use here, because this ends up being superheated. 1208.2 BTU per pound, and S3 ends up being 1.6830 BTU per pound times degree R. Okay, so that was easy enough to read those off. Now, the next stage, of course, is it goes through the second turbine, and it does so isentropically. So because of that, that implies that S4 is also equal to 1.6830 BTU per pound degree R, because it's isentropic. And we also know that P4 was 1 pound force per inch squared. Now, again, I'm going to have to go back through and find what this is, and what I find is it is a mixture again. So if you go to the table, you find that at this pressure and this value of S4, I am quite clearly in a mix. Excuse me. So I need to do the same thing again. I need to find the quality. So that's going to be S4 minus SF. In this case, SG minus SF. I probably should label those with 4s so that it's not confused with an earlier part of the problem, but I'm going to trust that you can figure out that those are from the same part of the table as S4 is. And so now I'm going to get 1.6830 minus 0.1327. And that's going to be divided by, again, this is the quality equation. You should know that at this point. 1.9779 minus, that's my SG, minus 0.1327, and I get something like 0.84. Now again, I'm assuming isentropic here, so this means my H4S, I can find it, but I need to use, again, the fact that it has a quality of 0.84, obviously, to get it off of the tables here. So H4S is going to be equal to HF plus 8x4 times Hg minus Hf. And that's how we do that quote-unquote interpolation when we have a quality as normal. 69.74, that's my HF, plus 0.84 times 1105.8, that's my Hg, minus 90. 69, sorry, 69.74. Which was obviously my HF. And that comes out to be approximately 940 BTU per pound. Okay, so that's what I have for that one. And again, my H4, just rewriting the equation, that was equal to H3 minus eta of the turbine 2, which we also had 85% efficiency, times H3 minus H4S. Remember, this was assuming isentropic. That was what where we would have landed if it had been isentropic, right? That's essentially the way to think about that. So that means that H4 is equal to my H3, which was 1208.2. We had already found that earlier off the tables, minus 0.85, because it was 85% isentropic efficiency, times 1208.2 minus 940. And this comes out to be approximately 980.2 BTU per pound. Okay, so now the final thing is we want to find, obviously, we want to find the work for each of the turbines, and etc., and the heat. But all of those just require H1, H2, H3, H4, and that's it, right? We only need those. So our equation before, W dot turbine 1 over M dot was equal to H1 minus H2. We were given M dot as being 120,000 pound per hour, which is a convenient unit because it works out with the BTU per pound, right? And we get something in terms of BTU per hour, so that's nice. So that means that my work that's coming out of turbine 1 is going to be equal to M dot times H1 minus H2, which is equal to 120,000 times 1388.5. That was something we found on the tables, if you recall, minus 1047.06, which gives me 4.097 times 10 to the 7th BTU per hour. The pounds cancel because it was BTU per pound and times pound per hour, and you just end up with BTU per hour. Similarly, for turbine 2, that's going to be M dot, and that's going to be H3 minus H4, which equals, again, the 120,000 times 1208.2 minus 980.2, and that comes out to be about 2.736 times 10 to the 7th BTU per hour. The net power, W net dot, is going to be equal to W dot turbine 1 plus W dot turbine 2. Notice both of them were positive quantities, so obviously it's going to be a larger quantity. And that just, if you add the two together, you can obviously do that. 6.833 times 10 to the 7th BTU per hour. That was the network, and that was what we were asked for that part. And then Q dot over Q in dot over M dot, we found to be equal to H3 minus H2. If you go way back up here, H3 minus H2. So that implies, of course, that Q in dot is equal to M dot times H3 minus H2. And that means that Q in dot is equal to 120,000 times 1208.2 minus 1047.06, which comes out to be about 1.934 times 10 to the 7th BTU per hour. Okay, so those are my two final quantities. That's all that I have for this video. Hope to see you again soon.